My code isn't always good. In fact, sometimes it's quite bad. Can you help me out? Can you help me spot the bug? Well, that's exactly what we're here to do today. In today's session, we're going to be presenting you with some code that is very interesting, but also contains some very small, very simple, but also very perplexing bugs. And hopefully, you're going to help me spot each and every one of them. But first, here's our agenda for today's session. I'm going to walk you through a couple of bugs and give you an opportunity to try to spot the bugs, to see what's wrong with the code, and to see if you can find in each and every case, it's a one-line change, the change that you would need to make in order to make the code correct. I'll give you one or two hints along the way, and then I'll provide you with the answer. But it'll turn out in each and every case that the answer is not the most important thing. The explanation is, the understanding, the steps to debugging, the ability to spot this bug in your own code, to not only fix it in your own code, but to know how to avoid it in the first place. This is a bug about non-determinism. Let's take a look. I have some code. The code is a little bit fun. It implements a simple analysis for a game of Scrabble. The idea is, can you play the game of Scrabble and see a pattern of tiles on the board and figure out, can you make a word fitting your tiles into that? There's a couple of limitations to how you might do that. You're looking only at words of maximum length 7, but for the most part, the analysis is reasonably sound. Because this is analytical code, I want it to be deterministic. I want this code to be repeatable. I want the results to be replicatable. In order to make this code deterministic, I've used a seeded random number generator. But when I run this code multiple times in a row, I get different results, and I shouldn't. And so here, we'll see the first run, it takes a moment for this code to run. And when we rerun this code, what we'll discover is the numbers will change very, very slightly. The code is available to you. I'll maximize your view of it. And the question is, can you spot the bug that is resulting in this code not being deterministic? I'll give you just a moment. Now, for those of you who've seen this bug before or have maybe thought of it a little bit, please do share some of your thoughts and comments together with the rest of us. But I'll give you one small hint. When you take a look at the code is pretty straightforward and it does the analysis as expected. There's a bit of analytical code at the end that's not related to the bug itself. But if we take a look at one small portion of the code, specifically the use of the collections.counter, and we were to isolate this bug and to see what happens when we give, for example, a Python set to a collections.counter, we can see that the ordering here seems to change every time I run my programming. And this matches up a little bit with the differences in the ordering that we might see when we run the original program. Does that give you a hint as to what the bug is? Well, here's the answer. When we write Python code, one of the things that we need to keep in mind when we're writing code that needs to be repeatable, deterministic, so that's either analytical code or maybe even testing code. You want your test results to always give you the same general outputs so that you can check, are these outputs matching exactly, or is there maybe some noise from some sort of environmental consequences, maybe environmental variables, a random number generator, the state of the virtual machine you're running it on, whatever the case may be. If you happen to write any Python code and that Python code happens to include machine-ordered structures, which in contemporary versions of Python are just the set, you have to make sure that you're operating on that set in a deterministic fashion. And it is very easy for the non-determinism of that set, that is to say, the purposeful randomness of the ordering of that set combined with the machine ordering of that set to cascade through your program in very unexpected ways. And so the nature of this bug is simply that when the person wrote this code, when I wrote this code, and they created a collections.counter off of the set of unique words that they pulled from user shared dictionary words, well, they didn't sort it. And that collections.counter pulled in each one of those words, processed them, even though the collections.counter might appear to order these elements in order from most to least common, In fact, the internal ordering represents the internal dictionary ordering, and that internal dictionary ordering is insertion ordering. Well, this will represent the non-determinism. And that's the answer for our bug. But like many of these bugs, I think a little bit of further explanation is warranted. And so let me break this down to the absolute basics. Here's what we have in Python. We have different collection types, and those collection types have, among their different aspects, an aspect of ordering. And so if, for example, we have a Python list, well, we know this Python list is ordered. And we know even more specifically that it's ordered in a way that we as a human being can use that ordering in our program. If we see a list with the elements 1, 2, 3, and 4, we know when we iterate over this list that they will be iterated over in that order that we can see. And we can use that ordering. This is why we might call a structure, like a list or a tuple, human ordered. Historically, in Python, types like the dictionary were machine ordered. That is to say that in early versions of Python, from Python 2 up to about Python 3.5, 3.6, the dictionary type used to be machine ordered. Now, that isn't that it isn't ordered. It isn't that this type doesn't have an ordering. It's that you couldn't predict what the ordering was. So in older versions of Python, when you would iterate over a dictionary, you didn't know if it would iterate over the keys in the order ABC, BCA, CBA. It wasn't a random ordering, and it wasn't an absence of an ordering, because if you iterated over that dict multiple times, you'd always get the same result. It's just that you couldn't predict what that result would be without having to know a lot of details of things going on behind the scenes. So in effect, you couldn't use this as part of how you designed your program. Well, as of Python, I want to say 3.8 and later, because this took a couple of different versions. In 3.6, a change was made. 3.7, that change was made to be something you could rely upon. So maybe 3.7, 3.8, and later, you can actually rely on the dictionary now being, so I'll put Python 3.7, the dictionary is now insertion ordered. And by insertion order, what we mean is the ordering of the elements of the dictionary, when you iterate over it, will reflect the order in which entries were added or the order in which these were specified when you have a dictionary literal. And so you can see no matter how I run this program, I'll always get those dictionary keys in the order A, B, C, because that's how it's written in my program. And if I add in another entry here, D, it'll always come at the end because it was the last entry that was inserted. However, you may know that the Python set type was originally based on the Python dictionary type. It was effectively just the code for the dictionary with any references to things like values removed. And the optimization that made Python dictionaries human ordered, that made them insertion ordered, was not really applied back to the set. It wasn't quite relevant. And so, in Python today, the set type is the only remaining machine ordered type. And so, if you have a Python set with the elements A, B, and C, and you iterate over this set, you have no idea a priori the order in which these elements will be printed to the screen. You'll see sometimes it's CAB, sometimes it's CBA, sometimes it's ABC. It's not just the case that it's machine ordered and ordered by the hash value of these entries, but it's also the case that there is some additional randomization added by your Python interpreter and some changes that you might see over the course of different Python interpreters or different versions of the Python interpreter for how that hashing happens. That doesn't mean that you can't control this order, and it doesn't mean that this is unordered or that this is randomly ordered. Because just like I said about the dictionary historically, if you iterate over a set twice within the same program, that set will show exactly the same ordering. And the only way that the ordering that you'd see here and the ordering that you'd see here could ever be different is if you went into that set and you changed it in some fashion. So for example, if I added a bunch of elements in the set and then removed them, what we would anticipate might happen is this thing might be reallocated, and when it's reallocated, it might copy everything over, and when it copies everything over, the ordering of these things might change very subtly. But if you don't change it in between, you'll always get the same ordering. Well, this is something that you can control, and something that if you want your tests to be deterministic, or if you want your analysis to be deterministic, you probably should control. One of the ways you can control this must happen external to the actual running of this program. In other words, there is an environmental variable, Python hash seed. And when you set Python hash seed, it'll actually set the seed that's used for determining how it's going to compute the hashes, and that'll fix the set ordering. The set won't be human ordered at that point. You won't be able to predict that ordering, but it'll be a consistent ordering that repeats however much you run your program. And you can see here, I might have to Python hash C, I might have to spell that correctly. There we go, and now we have a consistent ordering. And so, if you have a test runner or if you have an analysis, you probably want to make sure that you set that. However, the nature of this problem is a little bit tricky because it's very likely that maybe in your environment that's a little bit hard to set. It may be the case that you have some code that you want to have somebody run and you don't want them to tell them to set a bunch of environmental variables because they may have no idea how to do that or how to set that, or you may not even control that. Consider, for example, if you're running code using Jupyter, well, you don't really control how those environmental variables are set before the Jupyter Notebook starts, and this environmental variable must be set prior to the start of the interpreter. It cannot be set any time after the interpreter is already started up. Because you can think that as part of the interpreter startup, there's already a bunch of places where it needs to create things like sets and needs to use this. And so this has to be a change that you introduce at the earliest point possible, which may not be possible in all of your cases. And so you may need to apply some additional diligence. I want to take the original code that we looked at, and I want to show you how we might go through that code and try to identify places where that non-determinism might be creeping in, where behaviors like that might be creeping in. Because it turns out that the fix that I suggested, that is to say, you take this one line here, which constructs a counter object from a set of words where the ordering of that set is changing the ordering of insertion order in that counter, which is then changing how this random.choice picks which letters it's going to pick in order to create the different samples that you're going to test against. Well, all of that kind of cascades down to the actual non-determinism that you visit. And so what can be kind of tricky here is you might think that this is where the problem occurs, or this is maybe the most direct case where the problem occurs, but it's really a consequence of this structure, which is a consequence of this piece over here. So how do you find these spots in your code, and how do you figure this out, and how do you eyeball this? Well, here's a little trick that I have that you might be able to employ in order to debug these things in your code, in order to be able to spot these kind of issues and to be able to handle them or be able to address them. What you might do when you're running through your code is you might want to say, okay, I want to look for places in my code where across different runs, I'm getting different results. I'm not getting the exact same result. Now, obviously, anytime you work with an external resource, well, that's going to be tricky because you don't control that external resource. If it's a REST API, the endpoint can change all sorts of things all over the case. So what you're really looking at is in the inner parts of your program where you control all the data input and the data output. Everything is referentially transparent. Everything is pure. There's no aspects of global state or anything that you can't control. Well, in those aspects, are you getting exactly the same results? Well, here's a little trick that you can use. If we use the pickle module, we can take Python objects and we can dump them to a string. So we can get a representation of those Python objects. And for many of things like the built-in types, that will include the ordering of how these entries are stored within that structure. We can then go into the hash lib in the Python standard library, and we can grab a hash like SHA-256. And then what we can do at parts of our program, for example, if we go all the way down to the end of this program, we look at our stats, we might do something like this. We might say pickle the stats object here, take a hash of that, get the hex digest of that, and print it to the screen. And it gives us a way to start eyeballing these things. Now, just to make sure this thing runs a little bit better, I'm going to reduce the total number of test cases that we do. And this may actually cause one small other bug with the mean here. So we might just do a little trick here just to get this to work nicely. Put at least one value in that. Oops, and then we'll just make sure that we unpack this correctly. So there we go. That should run just a little bit faster, and we should be able to see, the hex digest of this structure. And across multiple different runs, we can check to see, we can eyeball that and say, is that value changing or not? And so here you can see, well, you know what? These hashes are actually pretty good at distributing among the space, so we don't even have to look at the entire hash. We can look at the last 6 digits. Kind of like when you are working with Git, the commit hashes, you don't have to give the entire commit hash. You can give the first 6 digits or the last 6 digits. So we can see 444 BB185. We run this again, and we can see, is there a change in this at all? Now, of course, we're looking at, in this case, the dictionary with the entries, 4BB185. It seems like there is no change here. Well, for this particular analysis with this number of entries, there might not be a change, but we might see one. So we could kind of go a little bit further up in the program and see if we can find a change a little bit further up. So here, let's put a sys.exit, just so we can get to that pretty quickly. We can see, did the samples change across the course of the runtime of this program? And if we do that, we can see on one run, it is, let's give this a moment to run, 527,531. Let's give it another run and see if we get the same result. 527,531. So you can see this is now running deterministically. We can go back up to the patterns. And we can take this idea all the way up until when we find that non-determinism, or when we find something that's changing. And that can give us the ability to triangulate and find this. Now, in the case of this, we already have Python hash seed set, and so you can see that these are giving you consistent results. But if you didn't have Python hash seed set, if you're in, for example, your Jupyter Notebook environment, you might be able to use this to figure out exactly where the divergence is happening quite quickly. You could, of course, incorporate these with other sorts of techniques, other sorts of introspection techniques, and that would give you the ability to say, okay, this is exactly where the non-ordering of the set is causing the end result to be non-deterministic. And as you review this bug, as you go through this code, one thing that you'll discover is there's actually quite a few other things going on in this code. There are other places where sets are used. Here, there's a set used in order to get the playable words, the words that you could actually play for this game. But this set is not the cause of the non-determinism. And so the approach for tracking things back might be necessary because it's not the case that you have to completely ditch the use of your Python set. It is the case, however, that you have to be very careful in places where the ordering of that set might be used for something that then might be used for something that might be used for something where that ordering might cause some issues. And so that's why, as part of this analysis, if we don't have Python hash seed set, we might need to sort this so we always get a consistent ordering. One other thing that you need to be aware of is just sorting your data may not always be enough. Remember that the Python sort is a stable sort. And so if you have some rich data that you're sorting, and that rich data comes from, for example, a Python set. So let's say ABC 123 and DEF 456. And we do a sorting of this. We'll get a lexicographical sorting of this. So it'll first sort on the first key, and then it'll sort on the second key. So we'll always get the exact same order. So it seems like everything is fine. Well, what if these two elements are of identical value? If these two elements are of identical value, then the sorting, or sorry, not those two elements here, but these two elements here are of identical value, we might see some non-determinism because the order in which these things will appear in the original structure may stably, sorry, I'll put this here. We'll actually have to make these identical like this. So we need to actually put one more thing in here that's not included in the seed. So here we'd have to do something like this. To really show this example, we'll probably need a custom type that has 3 fields where only 2 of those are actually used as part of the sorting condition or part of the hashing condition. So here we'd have field A, B, and C. And we'll say the hash here and equality are only based off of fields A and B. And this is just like this. And we'd say where equality was only based off of those fields. So this thing has one little field off to the side that's doesn't seem to be used for anything that's related to hashing or equality, but does contain some payload of important data. For example, something that might be stateful. Well, in this case, you might see across multiple runs that, and by the way, these things actually should hash to different things. So we get 2 different entries here. Yeah. So here we'll get two different entries. Well, when we see these two different entries, if we only sort this on a key that looks at only A and B, well, what we're going to see is these things will come in different ordering. So one of the things we have to do when we're doing this sorting is we have to make sure that it covers the entirety of the data, not just certain keys that might be important for that data. So we might have to actually create custom key functions that force you to sort on everything.